Hi, everyone, and thank you all for joining us today for Inspiration Exchange Session 51. We're really excited to run the session for NeurIPS 2025. Highlights a session ahead of the conference next week. My name is Marika, and alongside Antonin and Professor Michaela van der Schaar, we are your hosts for the session today. So in today's session, it'll be in two parts, like usual. The first being the presentation by our four students who will be presenting their works at NeurIPS this year. We have Claudio, Chris, Qiyao, and Silas. And after that, we'll be having a panel joined with our experts from industry, collaborators, researchers who will discuss the broader impacts of the NeurIPS paper presented. And so thank you all for your insights today. Before we dive into the papers, we wanted to briefly set the stage of what is NeurIPS. And so NeurIPS is Neural Information Processing Systems. And it is one of the world's largest and most prestigious conferences in machine learning and AI. It is highly selective, highly influential, and attended by top researchers and leaders from both academia and industry. And this year, NeurIPS will be held in San Diego from December 2nd to the 7th. So timely. We are very excited to have a number of papers from our lab accepted from the Van der Schaar Lab. And you will notice that here, Harry's paper, this was already presented in a previous Inspiration Exchange, IE49. So that won't be represented today. But we'll be today focusing on these four fantastic papers, which will be presented by Claudio, Silas, Qiyao, and Chris. And we've also put together an explainer article that walks us through some of the ideas of behind the paper. So if you'd like to check that out right now, you're able to access that through our QR code. And this is really exciting. We've also got Professor Michaela van der Schaar invited for two workshop talks, both on Saturday, the first one being AI for Next G, and the second one being Core Science. And if you are attending NeurIPS, we will be hosting a networking session on Friday, December 5th. So you'll be able to network with the students presenting their work as well. So we hope to see many of you there. And with that, I'll pass it on to Antonin to present the students.
Thanks, Marika. Let's jump right in with Claudio, student from our lab, that will present his paper, Cascaded Language Models for Cost-Effective Human AI Decision Making.
So, hey everyone, my name is Claudio. I'm currently a second-year PhD student here in the Van der Schaar Lab. And today I want to talk to you about my paper that is titled Cascaded Language Models for Cost-Effective Human AI Decision-Making. Let me introduce to you what the problem is that we are trying to address with this paper. So the overall challenge is that deploying large language models in high-stake environments, such as in medicine, finance, or education, often requires balancing three things: accuracy, cost, and uncertainty. Now, three sub-problems arise from this here if we want to decide what models to use, and that is basically larger models. They perform very well, but they come at a very high cost because more inference time, compute, larger reasoning traces, so they can become quite costly. Whereas on the other hand, smaller models, they are low cost, but often tend to have less good of a performance. Finally, a third problem that is addressed in this paper is, well, when should these models actually abstain, and when should a human be included in making a decision? So with this, we set up to build an AI system that is, first of all, cost aware and is also risk sensitive to the decision. And it needs, again, to learn three things. The first one is, when do I trust a response of a model, and when should it be escalated? So when should it be escalated to a stronger model? This is also based on the trust from before. And finally, at what point Should we abstain from answering a question, and should we rather get a human review? So these are the three things that we want to build, or that we aim to build in this project. All in all, the problem can be boiled down to this comic that I'm showing you right here, where we have our cascaded model framework sweating on making the decision between a cheap but dumb LLM, a smart but expensive LLM, or a human expert. For this, we set up three framework desiderata that need to be upheld when trying to solve this. The first one is we want to reduce unnecessary regenerations of answers. Let's assume a question comes in and it's immediately answered correctly by a large language model, a small one. We want to be that accepted and not to regenerate it with a larger one. So reduce unnecessary generation. Second, we want to abstain and escalate to humans when uncertain. Now the keyword here is uncertain. And finally, what is also especially interesting here is, well, we want this to dynamically improve because we get additional information if we involve the human and get feedback if we abstain. So this feedback should be used to improve the model or the framework in general. We came up with this cascaded LLM framework that you can see here. And it looks a bit complicated, but I'll guide you through it. We have a problem statement that is initially responded by a base model or a small model. And then we come to our first so-called deferral policy that is based on confidence. Based on how confident we are that this answer is correct, we either accept directly this response or we regenerate this response with a larger model. This is the deferral policy, and again, it's confidence-based. Then we come to the second part, which is in blue, which is the abstention policy. And here, the critical difference is that it's uncertainty-based. And depending on how large the uncertainty is, we either accept the model response from the small or the large model, or if uncertainty is too large, we escalate it to a human. And if we escalate it to a human, that leads us to our third point, where we can use the feedback to refine the abstention policy as well as the deferral policy. I don't go too much into detail on how we implement this here, but to give you a rough overview for the uncertainty, we use a Bayesian logistic regression. All in all, we try to optimize the following three-dimensional optimization problem. We want to reduce the probability of doing an error without abstaining. We add a cost component to this problem, and we add an abstention component to this because we don't want to abstain every single question. I'll show you two slides for my results. The first experiment only focused on verification and trying to find out what is a good method to learn on how certain we are of a response of a neural network. And we tried various methodologies there. And what you can see always in blue is only using a base model, and in green only using a large model. And you can see the cost on the x-axis and accuracy on the y-axis. Now in all these cases, often or most often, the black cross outperforms, and that is the so-called surrogate token probability by using a large model to verify the response of the low model. More details of this is in the paper. A second demonstration of our experiments that I want to show you is if we have a dynamic system where we have multiple question answering data sets such as ARC easy, ARC challenging, multitask language understanding, or two medical question answering data sets, we can see that the cumulative risk of this framework, if we use a base or a large model, accumulates risks quite a lot over time. Whereas if we use the cascaded system that improves itself with the feedback, it stays in all cases lower than a single model approach. Now with this, I want to conclude on why is this research important that we conducted? First of all, it's important because balancing the cost, the accuracy, and the uncertainty is important in these high-stake environments. Why is this difficult? Well, compared to traditional machine learning problems, we are now looking at this three-dimensional optimization problem and not just trying to perform the best in accuracy or the best in cost or uncertainty, seen as a single entity. And finally, why is this innovative, this work? Well, with this work, we were the first to introduce this cascaded LLM framework that is based on confidence and also based on uncertainty. And it manages to optimize the problem and also improve itself. With this, I want to come to my closing remarks, and I want to thank you very much for your attention. If you have any questions, you can post them on the Slack or email me, and a lot more detail about methodology and experiments are found in the paper. Thank you so much for your attention.
Great. We'll move on to our second presentation from Chris, who will present his paper, Simulating Viva Voce Examinations to Evaluate Clinical Reasoning in Large Language Models in the NeurIPS benchmark track.
Hello, everyone. My name is Chris. And yeah, today I'm going to talk about how to test whether a language model can actually, perform clinical reasoning and clinical examination. So the problem is that currently, most of the benchmarks, including, for example, some of the ones that Claudio introduced in our last presentation, all of them are question and answer benchmarks. They are mostly just testing for knowledge. They are only one turn, and we actually get the full picture. But this is not what it's really like in real life practice. So in real practice, what happens is a healthcare professional, a doctor, for example, they will really have a patient, they will come in, they will mention something that may or may not be actually related to what they actually have a problem with. And then the whole process of a clinical workup in practice becomes a game of detective, where you actually have to ask over multiple times and form, to some extent, a hypothesis of what you think the patient's problem is. And then afterwards, you need to then actually, not just ask, but also examine and also investigate. So in detail, like the real life practice is limited information, is multi-turn, and also what it requires as a result is what we call a sequential reasoning over a long horizon. And this is significant because none of the benchmarks, as of writing the paper before, had any of these, reflect any of these properties that a good benchmark should have to reflect clinical practice. And this actually has significant implications because on the right side is a real trace from one of the models that our benchmark. What we see is that if the models are unable to actually reason through this long horizon, and then they might get guided towards the wrong picture, then they might miss an important diagnosis, which, for example, in this case, they missed a heart attack because they thought the patient came in with some abdominal pain, which is an unusual but not impossible presentation for a heart attack. And then afterwards, they thought it was a gallbladder problem, cholecystitis, which is not, which is, in fact, the patient actually has an inferior myocardial infarction, which leads to sometimes presents with abdominal pain. So therefore, the key research question I came across to develop this benchmark is to test whether these models, whether these LLM agents can actually perform reasoning and not just recall medical knowledge, and whether they can perform reasoning under uncertainty, under a long horizon, and be able to actually actively gather the information. So how do we go to actually then simulate this then? So we're very inspired by in clinical, for all doctors and go through medical training, they have this exam called the Viva Voce exam. It's very similar to what PhDs go through, but for us doctors, what happens is it is an interactive oral examination where then the examiner on the other side will just give you a patient, and then it's mostly language, fully text-based, and then you have to answer question and answer over multiple turns, and you have to ask for information from the examiner. And if you don't ask for a specific thing, the examiner might not provide it to you. So this is multi-turn, it's interactive, and it's text-based. And I just thought it would be a very good medium to simulate for language model agents as well, to see whether they can actually perform clinical reasoning. So, and in more detail for our data set, what we did is we collected around 1,000 physician-curated data set, which are all public case reports of various difficulty. And then we developed a framework to convert it from unstructured free text to a structured information. So this data set is firstly open source and public domain, but also it is expandable, in which, if you have any clinical data yourself, you can also use our framework to then expand this data set to make the benchmark even more bigger. And then afterwards, now that we have a data set and we have these structured clinical cases, we then actually use them to convert to test the agents. And then the actual evaluation process is very straightforward. You have a very short stem, like for example, 30-year-old came in with some presentation, and then afterwards the agent they need to actually slowly and ask, first review the patient through a history and physical examination. And then we strictly limit it to patient workup first. And then afterwards, we ask the agent to provide a provisional diagnosis, which is what they think when they only did the history and examination. And then afterwards, we then ask them to then order the relevant investigations that could then help them isolate their diagnosis, which is a final diagnosis. And as a control, what we will also do is we provide all the agents with a full picture, and then ask them to actually provide the diagnosis with the complete clinical picture. And we see if there's a gap. So we tested 6 different state-of-the-art models with a mix of open and closed source. And the final thing we monitor them on essentially is the diagnosis code. So we asked them to do ICD-10 codes up to 5 different diagnoses at each point. And we also asked them to give us how confident they are with each of the diagnoses. So our metrics on this benchmark as a result is the diagnostic accuracy, top 1 to 5, and also at different stages. But also the 2 other things we do is we actually measure what kind of queries they ask. So what we want to measure, not in addition to how accurate they are in diagnosis, is also how good they are at actually seeking information. So we want to see what they ask for, whether they are relevant to the diagnosis, and also whether they are precise and not just shooting their shots randomly. And lastly, we also actually measure how confident they are with their diagnosis. So these are the main metrics, and let's see the results. So in this benchmark, the top models are usually the bigger closed source ones in Gemini, and the worst ones is some of the smaller open source ones. So in this case, Llama 4. But most significantly, there is a significant gap between the final diagnosis, which is where they actively seek information, and the full diagnosis, and it's literally doubles. So what this means is that these models, when they're actually given the full picture, they are very competent in making a diagnosis. They have no problem in identifying the relevant knowledge. But then the problem is when they don't have the full picture, they actually don't know what questions to ask in order to find the answer. And also, most importantly, a lot of the models are also confidently inaccurate in terms of what they think they know. And I will go into details in the next slide on why that is the case. So firstly, another aspect is also that we find out that most of these models, they are quite good in general at having so once given an initial prompt, they're good at having an initial picture, but then afterwards they are unable to then change their mind or change their hypothesis because they are very preconditioned with an initial picture that they keep on asking the same questions. So they're very selective in what they ask for, but they're not very wise in then actually manage to change their minds. And what we found out is that the ones who are best performing are able to some extent, add or remove diagnosis and also calibrate how confident they are. Whereas the ones who don't perform as well, they're very stuck on the initial picture and that's it. And they're literally unable to change their mind. And that's to some extent a confirmation bias. And in addition to that, we actually then looked into why they failed for the cases failed. So we actually human and then some LLM reviewed around 700 cases. And what we found out is that a lot of them, the majority of them is actually not from knowledge errors, but actually from reasoning. And in particular, there are 2 different types of reasoning errors that really reflect what humans fail at as well. So firstly is what, as I mentioned in the previous slide, they're very likely to just fixate and anchor on what they think initially it is. And then even if you give them let's say they think it's disease A, they'll give an ordering test only for disease A. And even if all the tests are negative for the disease, they are unable to just change their mind and say, what if it's actually disease B? So that's one anchoring bias. And the other one is premature closure. So what happens is sometimes a condition might actually be because of disease A, but they might be because of a more severe disease in the background. But once they have found out that that the patient is positive for something, they will actually stop screening for the more complicated things. And these 2 are actually very common in, I guess, real life clinical practice as well. So I find that quite interesting. And lastly, also, obviously, there's a 12%, a small amount where the agents also actually just unable to manage to order the right tests for the right diseases and unable to follow the protocols. So this is probably acknowledging, but most of the results so far we observed is that those are mostly reasoning errors in this benchmark. So yeah, so in conclusion, yeah, for this paper, our main contribution is that we have developed an open source and extendable benchmark to perform long horizon clinical reasoning. And through this, I guess, multi-step benchmark rather than single step, we actually did observe that a lot of these agents are unable or have at least some difficulty in actually reasoning over long horizon and over statistic uncertainties. And I think in general, within the machine learning world, I think these sort of benchmarks are quite rare. And I think not just in medicine, but I think in general, there is probably, I think there should be a push for much longer horizon benchmarks, because that would really contribute to all the current research in agentic AI systems. And because one of the limitations, for example, right now is that, NAI agents, they kind of fail at around 20 steps max. And that's because most benchmarks do not optimize for that. And they're unable to really think about sequential reasoning. And also, most importantly, also to some extent unable to have some degree of introspection to really think about their states. And as observed by a lot of the models failing, being either overconfident or underconfident in their decisions. So yeah, and that summarizes my research for this paper so far, and thank you for listening.
We'll jump straight into the next presentation with Qiyao presenting his paper Semantic-KG using knowledge graphs to construct benchmarks for measuring semantic similarity.
Thanks a lot, guys, for coming today and tuning in to my talk. So my name is Qiyao, and this work is Semantic-KG. This is a collaboration with GSK, with Ed and Leah. Leah is here, I believe. If you are coming to NeurIPS, as you can see, I posted a little ad here below the authors list. So we'll be in halls C, D, and E. Poster apparently 1305, which is very, very crazy to see a 4-digit poster number, if you're familiar with NeurIPS. And we'll be presenting on December the 5th. So yeah, definitely tune in. So first of all, what is the problem that we're trying to evaluate in this paper? It's that evaluating open form LLM responses is a critical challenge. And that is also because we are using LLMs to generate open form responses in basically every situation imaginable, where we are using them for various LLMs as judge situations, pick your favorites. However, it seems like we don't really have a good way of sort of evaluating them. Now, there are two sort of very obvious baselines of how you could do that. One baseline is to use sort of NLP metrics like blue or rouge. The problem is that these metrics, because they're based on n-gram characteristics, they normally capture syntactic overlap and not true semantic meaning. And so, as you can see here to the right, I've sort of included an example where rouge sort of misclassifies two sentences, and you can like arbitrarily design these sentences to be sort of semantically similar and syntactically dissimilar, and vice versa. And rouge is not going to do very well on that. The second baseline is human-labeled benchmarks. But obviously, these are expensive, subjective, because they're sort of subjective to human opinions and not available for many specialized domains. So the natural question to ask is, can we develop a first of all, scalable, second of all, domain agnostic, and also, third of all, a sort of automatic framework that allows you to just measure semantic difference in any domain, and that gives you sort of fine-grained control so that you can sort of design these however you want. And basically, the TLDR is, obviously that's what we try to solve in this paper. The TLDR is that we use knowledge graphs. And with knowledge graphs, what we do here is that there are two things you can do with knowledge graphs. The first thing you can do is you can generate text descriptions of the knowledge graph. So that's what we're noting here with the original graph and the response. When we say, quote unquote response, we mean like text descriptions of the knowledge graph. That's the first thing you can do. And the second thing you can do is you can perturb the knowledge graph. So what we have here is if the text descriptions are text that are generated on the same knowledge graph, then we would expect those text descriptions to convey the same semantic meaning. So that's where we say the label equals 1, and that means these texts describe the same knowledge graph. On the other hand, in the plot down below, if the text descriptions are generated on different knowledge graphs, then we would expect these text descriptions to convey different semantic meanings. And we have label equals 0, and so they're describing different knowledge graphs. And to summarize our framework, what we do is we take a bunch of these we get a bunch of these knowledge subgraphs. We do perturbations, and so we end up with knowledge graphs that are the sort of corresponding to the same knowledge graph or corresponding to the perturbed knowledge graph. And then we generate these text descriptions. And hopefully at this point, you see that the point of doing this is that we can test the understanding of semantic meaning by testing, sort of by inputting these text description pairs into whatever method we're trying to test for. And because we know the ground truth is in the knowledge graph, we also know the ground truth semantic distance between these texts. And just very quickly, we generate a bunch of data sets across diverse domains. And here we show our sort of evaluation performance. So we, again, just as a reminder, the goal of this benchmark is mainly to sort of so that we can have a scalable and automatic framework to evaluate semantic distance between the LLMs. But we also included a bunch of NLP metrics and a couple of embedding models in there just to sort of evaluate the performance. And yeah, I'm not going to go into too much detail on the results, but as you can see, we sort of analyzed the results much more closely in the paper. But basically, the TLDR is that the performance really sort of varies based on which method and which perturbation that you're using. And also, the one sentence summary, the performance also varies depending on which data set and which domain you're in. So that might be another thing that you want to consider when you're sort of quantifying the distance in these domains. So what is the takeaway of this paper? Well, first of all, I didn't go into the results too closely, but there are going to be situations where LLM as a judge is not going to outperform baselines. And so, basically, obviously LLMs are pretty good at some of these tasks, but there are tasks where baselines are better than LLMs. So we basically I hope this sort of calls that we really need to understand more about this detection of semantic meaning and whether LLMs truly understand semantic meaning and most importantly, in which cases they don't, because in those cases that might mean we want to use other methods. One sentence, better semantic similarity evaluation methods and benchmarks. Yep. So just again, as a conclusion, this is Semantic-KG, and we'll be presenting this paper in NeurIPS benchmarks. Cool. And just very quickly, some future works. More complex relations and sort of more complex tasks. And thank you.
Great. Thanks, Qiao. And last but not least, finish with Silas presenting his paper, Timely Clinical Diagnosis Through Active Test Selection.
Yes, so my paper is really about when we talk about these kind of medical diagnosis tasks that kind of Chris has also touched upon, where we want some sort of AI to diagnose patients efficiently. Many models, what we think, are not really aligned to how clinicians basically reason and how they perform clinical diagnosis. one of the things we really care about in diagnosis is how early we can detect diagnosis. So both time-wise and also how many tests we order. Obviously, we want to save costs. But obviously, for many, many diseases with a particular focus on cancer in this infographic, how early we diagnose the disease has a massive option. A localized cancer can just be excised surgically quite often with very good treatment outcomes versus very advanced cancers that were missed earlier have very, very poor prognosis. I think the framework kind of naturally lends itself to ML as one of the kind of core pillars of medical thing, because essentially once you've diagnosed the patient, quite often the downstream management you essentially follow like almost like the textbook of the clinical guidelines that are available to you. But this kind of diagnosis process is really like shrouded in uncertainty. And some things that are quite evident across healthcare system is that quite often doctors just order over tests. In general, but then also they have certain expensive tests that are often not really ordered when they should be ordered because there are no clear guidelines at an individual level. In the last couple of decades, kind of we've seen this massive shift towards evidence-based medicine at the population level, which does improve kind of outcomes as a whole, but for some things like ordering specific expensive tests where there might not be that much data, it works quite well. A problem of all the current machine learning approaches kind of that we see that are being developed is that quite often they start with a kind of fixed set of data, and then they extract maybe some features from it, and they perform essentially a classification or maybe regression tasks, right, in a static setting of like this patient has the disease, this patient doesn't have the disease. Some models are able to classify multiple diseases or provide risk scores, but really they're not really aligned in a sense with how a clinician performs diagnosis, where you have this kind of sequential information gathering that Chris was already talking about. Of each time you acquire a certain test, it kind of changes your probabilities of each of your differential diagnoses. And then another thing which current ML models don't really do is they don't really suggest what's the kind of next test as a clinician they should order. They will just issue a static prediction. So what we've done in the first part is we've kind of thought, okay, like how can we kind of represent this kind of diagnostic process in a Bayesian form? And we think one way of doing this is what is called Bayesian experimental design, which essentially means it's a framework on like guiding how to select the next best test given your current information, because you want tests that essentially reduce your uncertainty as much as possible. You can either do this from an entropy point of view or from a KL divergence. So what we actually argue in the paper and also demonstrate using the LLMs is that actually probably using the KL divergence is better, because if you do it from an entropy point of view, you just favor these distributions at the extreme. So let's say you have a low risk, you order another test that regardless of the outcome, the risk remains low, then your entropy would appear high despite your test being non-informative. Versus actually what you want is you want to order a test, right, that if it is positive, it shifts you essentially across the decision threshold, because that is a truly informative test. So what we do for this is essentially what you want to do is you want to kind of model how your posterior evolves as a function of like what test outcome you observe, and then you want to pick kind of the test that is expected to give you this highest shift in the posterior. One problem we have for these things is that Bayesian experimental design works great in domains like physics, where you have good models of the underlying system, which, despite some progress on digital twins, we do not have for humans. So there are no essentially good ways of generating these things from models. So what we propose in this paper is that, well, actually, while we don't have an explicit, maybe mechanistic model that gives us all these test results, is what we can use is essentially use an LLM to kind of suggest what they think the samples might look like, because we know that they've been trained on huge amounts of scientific literature, including patient records, lab values, and whatever. And they can also provide dynamic risk assessments. The other nice things about the LLM is that unlike the other models we've touched upon, so let's say a decision tree that requires static input, the LLMs work quite well in a zero-shot generalization, as in we can just ask them basically on any context and expect to get a reasonable answer. And it has been shown over the years with many benchmarks that LLMs have a lot of clinical knowledge encoded into them, and they can pass, let's say, USMLE style exams. So the knowledge is kind of there, while the reasoning might not be. So what we want to do with this is we're really shifting the reasoning from the model internally to the output space by say, okay, instead of asking you directly what is the next best test, I'm asking you to like generate what you think the outcomes of the test might be and how that would change your risk prediction. And with that, I'm going to essentially, on a Bayesian way, select the test with the highest utility for you. Another nice thing about this thing is that while the LLM step inherently is a black box and we're not changing that, is by generating these kind of intermediate distribution, it provides a very principled way for a clinician to update test results if they believe that something is not unreasonable. We always just issue predictions rather than absolute things. And you could also iteratively use the framework, but override which test you use and requery the framework. Vice versa, because you know if a certain kind of risk prediction or hypothetical test outcome does not seem reasonable, as a clinician, you could in principle just override it, although you're probably more likely to just order the test you want to order and then requery the model in the interest of time. But it does give you this kind of extra step at the interpretability. So what we actually show is that the LLMs are quite poor essentially at this kind of thinking intrinsically how certain tests would change the risk estimates. We've used a variety of data sets with different conditions, and we compare essentially as baselines for this kind of feature selection and then issuing a prediction. And what we show is that this kind of probabilistic way of reasoning in the output space does a lot better than like baselines. Well, include a random baseline for just like a stochastic thing, but also these kind of global best and implicit baseline. Global best just means we ask the model at the start what tested things are best for the diagnosis without any patient information. The implicit is just at each step we ask the model, oh, what is the next best test you would like to order? And then we can see essentially that across the data sets, the model really struggles forming these probabilistic representations, and it's much better if you shift that to the output space. Yeah, I'd like to thank Mihaela and Nicolas, my co-authors, for this paper, and also Microsoft for sponsorship that enabled the compute. Thank you.
All right, thank you everyone presented for the great presentations, and we'll jump straight into the second part of our session, which is our panel discussion. We're joined by our four fantastic panelists, Leah Gutz, who's a senior AI and ML engineer at GSK, Alison Smithers, principal scientist at Canal Medical Research, Jeremy Voisey, senior scientist and team lead in the AI research bioinformatics team at Canon Medical Research, and Professor Ewan McKinney, professor in the Department of Medicine at the University of Cambridge. And without further ado, I'll give the floor to Professor Mihaela van der Schaar to kick off our panel.
Thank you very much, Leah, Alison, Jeremy, and Ewan for joining us for this panel. Anton, there is no need to display the slide. In this way, we can see each other better. And I'm going to start, if you allow me, with the last presentation, the presentation of Silas about timely diagnose. And I'm going to put on the spot the clinician in the room, Ewan, and Jeremy. You, because you at Canon are very interested in diagnosis and timely diagnosis. And so I want to ask the two of you about any comments about the work of Silas, and especially both from your point of view, how do you think it can be incorporated, indeed, tools like the one that Silas developed within the workflow of clinical practice to assist clinicians to do better diagnosis, but also where do you think we should go next? And what are the vulnerability with respect to that? And then I'm going to you, Jeremy.
Many thanks, Mihaela. First of all, very cool presentations, all of them. And so just to focus on Silas's, first of all, I think this area of active test selection is a massively important one. So the problem you're tackling is huge and real. I would make a quick comment, which is that the flip side, other than what you presented, is also very important. In other words, you're trying to identify what test I should do in order to expedite a timely and accurate diagnosis. I think there's huge grounds to be made in identifying what test I should not do, because we do a huge amount of unnecessary investigation that's very costly, invasive, So I think the same approach could answer both questions, and I think both sides are very important. Just to take what you're addressing, which is the early diagnostic window, that gets harder the further you go from diagnosis. So when you are being diagnosed with a disease and you have all the features, it's comparatively straightforward. I just line up the diagnostic criteria, I do the test that matches the criteria, and I get the diagnosis. Where that gets harder is the further and earlier you go back, and your slide was great on that in terms of showing the benefits of early diagnosis with better response rates to treatment. So I think in terms of pushing the next phase, trying to go further earlier into risk stratification, because your problem will change over time. If I go really early, the best test may be test A. If I go a little bit closer to diagnosis, it might be test B. It might not, or further on post-diagnosis for prognosis, it might be test C. So I think that will dynamically change. And the third complexity that I think would be great to address is that tests aren't done in isolation. They're not isolated units where I do this one, or this one. We do them in batches. I do a set of blood tests and usually get 15, 20 results back that are naturally grouped together in the way that they are sampled. So doing a test is not quite the same thing, and I get multiple pieces of information. And then every test I come back, I'm updating my own Bayesian clinically trained brain that says, well, actually, the updated probability of that is now this, and that will change. So I think you'd have to iteratively rerun the sort of algorithms you're describing, but massively important and really interesting. Thanks for presenting.
Thanks, Alan. Jeremy, I'd like to ask any comments from you, including whether I know you in Canon are building all sorts of imaging, machine learning methods that I think can be very nicely combined with the type of early diagnosis framework that Silas has presented. So, of course, one could invoke different types of tools a posteriori after, for instance, an imaging test has been done. But one could potentially combine the framework that Silas has presented with the type of analysis that you are doing in Canon. So I wonder whether you see a possibility about that as well.
Yeah, thanks. Again, I'll echo kind of very interesting talks, and congratulations to everyone who's going to NeurIPS. Where to start? It's just so many ways. Obviously, from my point of view, I'm also not a clinician, so kind of fascinating to kind of think about the thought process of the kind of clinicians. So what do they take into consideration? So you mentioned the kind of the imaging. So that's the thing which they would view, how you engage that into your reasoning model. That would be really interesting to see. So do you do that with like a simple visual encoder? Is that what you have in mind? Also, as well, then kind of I would like to see perhaps an agentic approach with what is the kind of information is the clinician going to fetch? What questions they're going to ask? That's something you might want to collect from the kind of EHR system. So, and also as well, I'm going to point out that differential diagnosis, like kind of, it's not just taking into account the kind of the question. There's so many kind of the risk factors you need to take into account. So how do you model that? I do know that there's been work being done by people to model the risk factors, the symptoms, how they link to disease, and that is a massive source of knowledge. Could you take that into account as well, that knowledge base? And I know that the models which they are taken into account are quite basic. It's a tripartite Bayesian belief network, and it's not very sophisticated. So how do you even start to take that into account in your modeling process? So I think there's a lot of work to be done in this area, but fascinating to see.
Thank you, Jeremy, for all the food for thought and all the homework you are giving to Silas. Yes. Thanks a lot. Let me move such that I stay with medicine, and then I'm moving a little bit further away. I'm moving now to Chris' presentation on these benchmarks for reasoning. And maybe what I'm going to put now, I'm going to ask first the perspective of you, Alison, not as the clinical expert. I'm going to turn back to you and ask you about how good a benchmark that is from a clinical point of view. But Alison, maybe to you as an expert in agents and large language models and looking at reasoning, any food for thought for us with respect to that? And also, what type of reasoning benchmarks you would like to see in this clinical machine learning space? What other exciting things you would think we would need to do? And maybe what makes a benchmark exciting useful from a medical point of view and exciting from a machine learning point of view, because that's, I think, a difficult balance to get.
Yes, thank you. I checked your background, Chris. You're a medic by trade, which gave you a bit more confidence in your data set. And this is a really great effort. So I actually have another student working in agent systems on exactly this problem of multi-turn conversations, and the fact that accuracy tends to degrade and you get sort of context rot. And yeah, no, it's a really interesting topic. So one thing I guess I wondered about was the fact that if a question is asked which is not relevant to the correct diagnosis, and values in the normal ranges are provided, or for test results which weren't available, it's stated that it's not available. And I just wondered whether this data set was somehow sort of easier than real world, which is messy, right? I believe in OSCE exams, doctors would be given a few red herrings or, sort of slightly messy data. And I would be interested to see how a human would perform on this data set to give us like a baseline to compare how your models are doing. Did you look into those things?
Yes, definitely. So to answer the first question,
It's very short because we don't have a lot of time. So very short.
Sorry.
Yes, of course. Yes. Yeah, so first question, yes, we provided both versions, but also the case report we selected for in the first place included a lot of relative negative. So that was one of the screening criteria. So if we have no EUCs, for example, then those will be included as the results. But otherwise, if there are specific tests that are not available, then they say not available. Generic results, then it would just be like I tried both versions. I tried not available and normal ranges. The difference wasn't significant because I noted that then the model in the reflection said this is negative. But I agree, I think some red herring would be good, but also I think one of the criticisms I already had was case reports might be harder. So I think it's a balance between hard and easy. To your second question, on human baselines, there was one of the things where I tried to explore was a much bigger human baseline, but I actually did get like 3 of my friends to do 14 cases. It's a very small baseline. I would say they are comparable to AI, I think better at the actually information seeking, and they're more comprehensive in what to screen for. So I think that's one of the bigger things that differentiates humans and AI. And I think maybe to as what Ern said, one of the things we do as clinicians sometimes order too much to cover our bases, but at least for this test, it's a sign that is a good thing because they were very comprehensive in ordering the things that might not even be immediately relevant. But it's also a balance.
Thank you, Chris. I'm going back to you now. Sorry for
not at all. I think totally fascinating. One of the most fascinating things is every characteristic that you described in your model as how it was feeling and getting it wrong is things that we see in trainees and medical students. It's basically making the same mistakes that training doctors do, which is really interesting from a epistemological point of view. So anchoring, premature closure, over investigation, those are very common problems. Very briefly, I would say that actually rather than be easier, I think you've selected harder cases than normal, but you've selected cases that have a clear, clean answer. So case reports by their very nature take the extremes and very rare, unusual presentations. The maxim that an uncommon presentation of a common disease is more common than a rare disease is something that isn't captured at all by your data. So in other words, you would consistently, maybe correctly, pick a rare diagnosis, whereas in practice, using an EHR real-world data set, it's more likely that that set of features may actually be due to a common disease that just has an unusual presentation. And we see that very commonly. So I think you would get a different nothing about the approach, because I think the approach is fantastic, really interesting. But actually, if you used a different training set, if you used an EHR data set where we know LLMs do very badly, they can't follow guidelines. And against that type of benchmark, they're very poor. I think if you did that, you get different results. It would be really interesting to see how they performed in that context.
Thank you very much. Let's move to Claudio. So clearly, large language models are getting better and better and better. Some of them are more costly than others and not available to others. And Claudio presented his ideas about this cascaded process. Maybe I ask you, Leah, and you, Alison, since both of you are working quite a lot in this area of human, both reasoning and human AI interaction. So I'll start with you, Leah. Any thoughts about how can we really make cost-benefit trade-offs, but also maybe not only cost from, I know, Leah, you are working a lot in the whole responsible AI area. So there is not only computational costs, there are all sorts of other costs as well. So how do you see this multiple large language models teaching each other, cooperating with each other, and improving their performance and improving their interactions with a human?
It's a really tricky question, actually, because one thing that people seem to value when interacting with models is some sort of transparency. For example, you get a reasoning, and then people prefer that answer to just the out of the black box. But obviously, if now you have this whole framework and you don't just have one model, but you sort of stack 10 on top of each other, that in some sense decreases the transparency of the system. So even if what comes out of it might be more trustworthy because you've got some self-critique approaches in there, etc., I think you might not actually get people to trust it more in the end.
Thank you. Alison and Jeremy, any other comments or any thoughts about what is next if it is to really build this more powerful approaches where one has multiple LLMs teaching each other and potentially having different cost benefits trade-offs and allowing for better interaction with the human? And any other comments on Claudio's work?
I mean, honestly, if we can get models which can perfectly estimate their own goodness, we've hit the holy grail. And because medicine is, predominantly normal, routine patients, and then you have the more rare, serious cases which you don't expect AI to have learned how to handle because they just won't have seen enough training examples. And if you can get very good at escalating those to the human, you've got a sort of perfect system where the human doesn't have to deal with, routine workload. And also by cascading LLMs, you can sort of optimize the amount of computational load, time the system takes, and so on. So, I mean, yeah, I applaud the effort. So
yeah, absolutely. This is going towards metacognition, isn't that definitely the holy grail? It's so it's the end of the day, the kind of LLMs, we train them to give a response that we want them to. They're autoregressive. We want them to give a response, and yet if you ask me a question, sometimes I simply don't know, and it's I don't reason through my head that I don't know. I'd simply get a mental block, and you almost want those large language models to do that, to have that mental block. I did notice as well. Interesting in Chris's work, there was a really weak correlation between confidence and accuracy, and I think that's great to kind of get some work in this area to try and understand the challenges ahead of us.
Yeah, I can only second that because especially after RLHF, LLMs tend to be quite poorly calibrated and overconfident. Perhaps better than the underlying probabilities, but still quite poor. So if we can make progress on that, like estimating the confidence, and then put that back in frameworks like you've described, I think that would be a big potential step forward.
Thank you so much. Last but not least, the whole work on semantic knowledge graphs. Leah, of course, I'll start with you. What is next in this agenda? What do you see as big, important follow-up work? And then any other comments, for instance, from Alison? Do you see this semantic knowledge graph benchmark being useful and in what scenarios? But maybe I start with you, Leah.
Yeah, sure. I think the next step would be really to try and well, first of all, extend it to more domains, and then also potentially make the statements that we're looking at more complex and closer to what you'd look at in the real world. But then why did we want this benchmark? To understand which semantic similarity methods we can use to evaluate other LLMs. So I think what we need to do is close that loop and actually use that benchmark to improve semantic similarity methods or LLMs that are supposed to do that task. So we have one that's really good that we can then use to automate the evaluation of the LLMs that we originally set out to do.
Sounds good. Alison, do you see this type of benchmarks being useful? Could they be useful, for instance, also to test reasoning of agents or other work that you see happening in this particular agentic area?
Yeah, I mean, I was smiling reading this paper because we come across exactly this problem that metrics like Blue and Rouge are not very good actually at measuring the quality of generated text. It was interesting the knowledge graph method for creating this data set. I wondered why not use that also to assess accuracy, because if you extract knowledge graphs from generated text, you can do this sort of comparison. Is the semantic content the same? And this is sort of the line that we've gone down in terms of metrics, not so much with the edges, but majoring on, extracting the nodes, I guess, and doing that comparison. Very valuable though. I totally agree with the effort, because we continually find that text generation, the style tends to be great, beautifully mimics a human response, but the content can be nonsense, and that might not be detected by our metrics.
Thanks a lot, everyone. I don't know whether there is any final comment by any one of you. Otherwise, thank you, Alison, and Jeremy, and Leah. But if there are any final things that have not been said and you want to make a final comment, please do. Otherwise, Anton, the floor is yours for questions from the audience, for the panelists and audience and the students.
Thank you. Yeah, thank you all for the fantastic panel discussion. Yeah, now we'll open the floor for any questions from our presenter to the panelists, or from the audience to any of the presenters and panelists. And our next session will be on January. We'll skip December for end of year holidays, but our next session will be mid-January on our Discovery Hub. You can find our session from today on YouTube in a couple of days, and feel free to visit our dedicated page to see all the previous talks as well on YouTube. And thank you all. I'll thank again our four panelists for the wonderful discussion and all the food for thought, and our four presenters for the great presentations. Thank you, everyone.